All right, guys, welcome back to another shift here at the Intensive Car Units. In this episode, we're going to deep dive into my plans and my ideas on how I'm going to get the Maserati Torque Tube shortened. In fact, I'm not. I'm going to go ahead and actually have my own made. And on this episode, we're going to break down on those key ideas on how I'm going to accomplish that and what vehicle I'm actually going to mimic. So sit back and enjoy. Let's talk about some of the challenges that I have to deal with for performing this swap on this vehicle. Again, I'm running the torque tube. I've had a few questions regarding some stuff, but before I get to answering the question on why the torque tube versus a conventional drive shaft, I just want to show you guys something and show you how much work this actually is going to be. And I don't want I don't want this to scare anybody. I just want to show how I'm going through this process. So let me spin this camera around and we'll get talking. One of the things I want to bring up is I have to make the torque tube flange. This guy out of aluminum. I could cut this off and just reuse the steel. It's a big heavy hunk of steel. But again, like I said, the entire assembly weighs 92 pounds for what I'm going to do. Instead, I'm going to make it out of aluminum, and I'm going to use the Corvette design, which is similar to this, but it has flex joints inside that make it work a little bit better. And I'll show photos up on that one while we're doing this. So what I want you to see is I've been using Fusion 360, and I have gotten the bolt pattern for this system. But the reason why I'm showing you this is because this is not my first attempt. This is actually attempt number 10 on my drawing, because again, I'm learning how to CAD and it's a process. So that's the transmission side of the flange, or transmission side, and then this should mate up to it once I cut these holes out. Now, the importance of things, you'll notice that there is a square right here. This is what I'm using for scale to make sure that whatever I've drawn is printed off at size. This is a big thing, and I'll explain why here in just a second. Because if this gets printed off and you have one thing clicked incorrectly, you could drop down the size of something very precise by 10%, 15%, and you wouldn't be able to tell without a reference mark. So Fusion 360, I created a reference. This is a 1x1, and it's actually a three-dimensional box that's 1 inch cubed, but it's on a drawing, so I didn't show that. Now, what that's allowed me to do is I can now take this, cut this piece of paper out with these holes to then test fit it on the transmission side to make sure that I have my bolt pattern figured out. And I am about 95% certain that I've gotten this part right, these 6 here, and I've taken this one out, but I'll explain that. But the two that I really struggle are these two. So I'm gonna have to get really creative on figuring out its location in relation to all of these other bolts. And there's gonna be a ton of measuring for this process. So I'm gonna go ahead and film me cutting out the holes. I'll time lapse it so you don't have to sit there and watch me for an hour and a half. And then I'm going to go ahead and test fit the thing on this, possibly get my marks lined up so I can then figure out what these are. And from there, I will then turn around and be able to actually make that flange in aluminum, which is going to be huge for weight. So sit back and enjoy. You just saw me cut out the holes for the transmission flange. Now, I'm doing this so I can literally come right over here and place it onto the transmission. And you'll notice it lines up almost perfectly. Well, perfectly enough for what is otherwise a pretty flimsy setup. But that lines up. So now what I get to do is I get to pull the studs off these guys so I can trace
onto this piece of paper to make the lower bolt pattern on here and make it nice and easy to where I can figure out what the actual distance is from here to here, and 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 you guys get the idea. That way I can actually figure out the exact location of these two bolts, because without those two, this whole, I'm willing to bet that Ferrari, Fiat, Maserati designed this with a purpose for these two bolts. So there it is. Okay, now we're going to show you a little trick with the tracing. So I'm going to put this guy on. I'm going to use my dirty thumb and try to get it relatively close to center. I've seen some people will use glue to hold it and then just drag the thumb over the edge. And by doing that, I now have trace holes for where it goes. Pretty neat.
Now, as you guys can see here in this photo that I've got, I had to, again, make circles on circles on circles so I get a rough estimate on the location of the actual bolt holes for that lower area. It's a bit of trying to find, Jupiter's orbit. But overall, I was able to figure that out successfully without too much trouble.
So way back in episode 5, I had a question of what are the advantages of using a torque tube over a conventional drive shaft, or as the Europeans call it, propeller shaft, especially with all of the amount of work that's involved with the torque tube setup. So to explain this, I need to bring in some algebra and some physics into the discussion, and I will try to talk about it in as simple as terms as possible, but I apologize if I sound a little too much like Sheldon Cooper or Rain Man. Now, before I get assaulted by the internet, I'm omitting some of the required pieces of the calculation used in physics to make it easier to understand without missing the key principles. The formula that I'm going to follow is T equals F times D. The first value, T, is called torque, which is a measure of the force that can be caused on an object to rotate on an axis. The second part of the formula is force, or F, and that is what causes an object to accelerate in a linear direction or a single plane. Third, D, the length or distance of the arm acting on the axis. Now in our scenario, the axis is the rear axle of the differential. That's the pivot point that the differential is going to rotate on. When this happens on a car, the front of the differential will move up or down depending on load or unloading of the throttle. This term is known as axle flip, and it puts an increased load on the connecting sections of the drive shaft, most commonly called U-joints, and or the differential mounts themselves. So if we have a short distance on which we are measuring the front of the differential going up or down, we would then have a larger amount of torque than if we lengthen out that distance. Think about opening a heavy door. If it takes less work and effort to push or pull on an open door, the farther from the hinges the door swings on. Now, because the torque tube increases the distance at which the front of the differential will lift or drop, the amount of force is reduced quite a bit. So much, in fact, that we can eliminate 2 drivetrain mounts from this design entirely over the conventional drive shaft design. This design also removes conventional U-joints that fail faster as the front of the drive shaft moves up or down when the engine, transmission, and differential are all solidly mounted together, eliminating any flex of the driveline itself, also reducing parasitic loss of power as an additional benefit. Another benefit of this design is allowing the transmission to be put in the back of the car, and by attaching the transmission directly to the rear differential, I can achieve better weight distribution, so much in fact that I might be able to achieve an optimum 50-50 weight bias in the Scion chassis. This should help us in cornering and putting down our newfound power and torque increase. It might even help with braking. Now, I hope that clears up some of the confusion on why I'm putting so much effort into this design instead of pressing the easy button and buying a conventional transmission and drive shaft setup that would then put more weight over the front axle. Again, the reason why I'm doing all of this is for the sole purpose of reducing weight, simplifying, and making this car more competitive up against the Cayman GT4s.
So in this picture, you're going to see the three different setups that we could use here. On the bottom is the factory Scion differential drive shaft assembly. Above that's what I pulled out of the Maserati. Big old hunk of steel, lots of bearings, lots of metal, pretty complex engineering setup, but it's actually a pretty pragmatic design. And then on the top is the Corvette, which is actually a similar setup to what I'm going to be mimicking. And I'll show you why as we get this thing torn apart. It's a lot lighter too. That whole assembly weighs in at 41 pounds, and we're actually going to remove even more weight out of that as we make our setup. So one of the nice things with the Corvette design over the Maserati is I can take this entire drive shaft assembly apart at the racetrack. I don't need any special tools. I don't need a press, any heavy duty machinery or components. It's literally held in with a little C-clip. Once I remove that, I tap the input shaft a little bit with a hammer. A rubber mallet will even work. This one was a little bit more stuck and required some more coercion than what normally takes. But once that's happened, you can pull that drive shaft assembly out and take it apart, address the rubber discs that you see me trying to break loose right there. Those are actually BMW parts. They are sourced directly from an OEM supplier for BMW for the E36, E46 cars. And you can swap these out with rubber. You can put in, they make polyurethane ones, they make aluminum ones just to reduce any flex if you want to run some serious power levels with that. But I won't need to do anything that crazy because I'm only running about 450 horsepower when this is all said and done. But again, you notice how simple this is. Add a little bit of heat, break loose that Loctite, and I can swap this out. I can, go to a manufacturer of the drive shaft and say, hey, I need this thing to be X inches long, and they can make it, right there on the spot in most situations because this is such a common vehicle, common drive shaft and everything like that. The main thing I had to do was just make those flanges and make the input shafts and output shafts for the actual torque tube itself. And once that's all said and done, just getting the drive shaft manufactured with off-the-shelf components, hopefully. So it's going to be a much easier, much simpler, and even lighter setup than the way Maserati, Fiat, Ferrari does it. And here you can see all of the components that are part of the drive shaft torque tube assembly for the C6 Corvette. And again, this thing weighs 42 pounds or so. So it's a 50-pound weight reduction over what we currently have. Okay, so there was a ton of information on that from engineering standpoint and a lot of physics and blabbing and stuff like that. I hope you guys have enjoyed this episode. Again, I wouldn't have even made this episode if it wasn't from a question that we had way back in episode 5. Now, if you think I'm on the right path, let me know. If you think I'm being a complete idiot, please let me know on that one as well. Because I'm here to make you guys entertained, well, at my own expense. So I look forward to seeing you guys next week or next episode, whenever that happens to get posted. And as always, please stay safe.